All right, we are now recording. Let me get the slideshow set up from current slide. And the first thing I want to know is if you have any questions on anything we've done up to now. All right, for those who may not have been here last time, we did finish 2.3, and I gave the quiz, actually at the time before, I think. Does anyone here not have a copy of the quiz? Okay. And then we started on 2.4, which you're not actually responsible for technically on the test, because if you look at the course description, it doesn't say a thing about complex numbers. However, it's not that they aren't important, that you don't need to know a little something about it. So what I'm going to do is just go over some of the highlights of it. You're not responsible for this, but if you ever need them, which the odds are you might need them at some point in the future, or at least you might run into them and you'll need to know something about them. So that's what we're doing now. So any questions before we get started? All right, now, the imaginary unit I, we talked about that last time. Can anyone give me a quick description of that imaginary unit I? Okay, you can't usually take the square root or any even root of a negative number, not in the real number system. So what else were you saying on that?
Anytime you have a negative number under an even bracket,
right?
It'll equal something with I.
Okay, it will come up with something with I, and the reason for that, what is I? It's what? It's the imaginary unit or imaginary number. I like to call it. This one calls it a unit, whatever. But what does it mean? What does it stand for? What value does it have? I is the square root of negative 1. Okay? That's it. The square root of negative 1. Not a real number. There is no real number who's the square root of negative 1. It's the imaginary unit. Another way to express it is that when you square this side of the equation, you get I squared. You square this side, you lose the radical. So I squared is negative 1. Okay? So that's actually what I is. I always thought it was IR, but no, it's not. Okay. By adding real numbers to real multiples of this imaginary unit, we get the set of complex numbers. Okay? And did I? Yeah, I think I went through this last time, didn't I? You started with what kind of numbers? The counting numbers or natural numbers. Those are the first ones you ever ran into. Okay, because that's what you did. You counted. And when you added, that's what you used. And your teachers were probably pretty careful to have you subtracting, so you used only the counting numbers there too. Except somewhere along the way, we needed one more little number that didn't count for much, 0. And that became then, when you added 0 to the natural numbers or the counting numbers, now you had the set of whole numbers. Okay? Now, probably several years later, when then you had to start doing signed numbers, you had the whole numbers on this side, nothing over here, and when you had to start subtracting big numbers from small numbers, that threw you in the negative number territory. That then, the combined whole numbers with their opposites, that became the set of, not yet, integers. Okay. And actually earlier than that, we had, when we got introduced division, not all division will come out with whole numbers, right? You sometimes would have fractions. Fractions then introduced another set of numbers, which was the rational numbers. Okay? Now, all integers are rational numbers. 2 is 2 over 1, a ratio of 2 integers. Okay? And that's what a rational number is, a ratio of 2 integers, as long as that bottom integer, the denominator, cannot be 0. Okay, as long as that's true, it could be, that would be your rational numbers. But then sometimes later, probably a fair amount later, you started running into numbers that well, actually what you started doing, you started squaring numbers and raising them to the third and fourth powers. After you did that for a while, then you started doing the reverse of that, the inverse of that, which is taking square roots, cube roots, and that kind of thing. And here we ran into another problem. What was that? Yeah, if it's not a perfect square and you're taking a square root of it, then there is no rational number that makes that. So then we introduced irrational numbers. Those are numbers that when you write them as a decimal, you neither terminate that decimal or repeat any part of that decimal ever. Okay? They just keep on going and going and going with never repeating any unit. That's an irrational number. So, when you combine the rationals with the irrationals, now you get the real number system. Now we're introducing something that does not include the real numbers, but by adding the real numbers to real multiples of the imaginary numbers, now we have a whole new set of numbers called complex numbers. And they have a little diagram in your book, and I think we're going to get to the slides, so I'll hold off on that. Each complex number can be written in the standard form of A plus BI. Okay? You tell me what the A's can be. All real numbers. Tell me what the B's can be. All real numbers. But then the B part, you're multiplying by that imaginary unit, which is square root of -1. Alexis and Allison are here. All right, good deal. Okay? And so we call this the real part of a complex number, and this is called the imaginary part of a complex number. So complex numbers are made up of two parts. Now remember, B can be all real numbers. Can you think of some little real number that doesn't have much value? Even less? 0. So B could be 0. What does that give us? Our real number system. Okay? So, all real numbers are complex numbers, but not all complex numbers are real numbers. Same thing we had with fractions and that kind of stuff. For instance, the standard form for a complex number, -5 plus the square root of -9. Okay? What is square root of -9? Okay, it's the square root of -1 times the square root of 9, right? Square root of -1 is I, and the square root of 9 is 3, so you're absolutely right. -5 plus 3i. The real part, the imaginary part. Okay? And they just did that here. Same thing I did, and that's how you get it. Any questions on that? Again, you're not responsible for this, except that if you ever need it, now you know what they are. Okay? So here's the definition of a complex number. Let A and B be real numbers, just like you said. Then the number A plus BI is called a complex number and is said to be written in standard form when it's written that way. Real part plus or minus the imaginary part. The real number A is called the real part of the real number, and the real number. Now, here's the part I differ a little bit on their nomenclature, as long as you know what you're talking about. They say the real number B, just the B part, is called the imaginary part. The B's a real number, so I call BI the imaginary part. This text calls just the B the imaginary part, and calls I the imaginary unit, so together go. So anyway, it's just a matter of semantics, I think. When B is equal to 0, like I just said, then A plus BI is a real number if B is 0. When B is not equal to 0, the number A plus BI is called an imaginary number. Okay? And again, that's sort of true. I call it a complex number. Okay? Because all these are complex numbers. But they say if the I is in there, then it is an imaginary number. And that's true. number in the form bi, where a is 0, okay, but b is not, is called a pure imaginary number. So if it has a real part and an imaginary part, then it's just called an imaginary number. This is how this book calls it. And if they have no real part and just the imaginary part, then they call it a pure imaginary number. Again, this is sort of a nitpicky little definition, and I think you'll find other texts that deviate from that slightly, but it's not a big deal. It's just how you call it, okay? Whether you call it Fred or Freddie, it doesn't really matter. So here's the diagram of this. The set of real numbers is a subset of the set of complex numbers. Complex numbers are all these numbers. Those that are real only are real numbers, and those that have an imaginary part to them, those are imaginary numbers. Now you could back this up and have rational and irrational feeding into reals, and then you could back that up and have integers and others feeding into the rational numbers, and you could go back to all that we just talked about. Okay. Now, this is true because every real number can be written in the form of a complex number using b equals 0. A plus 0i. Yeah, that would be a complex number. It's also a real number. That is, for every real number a, you can write a is equal to a plus 0i, making it a complex number as well. Again, what's the big deal? So, what do we mean by two complex numbers being equal? Two complex numbers, a plus bi and c plus di, okay, written in standard form, are equal to each other if and only if, okay, a is equal to c, in other words, the real parts are the same, and b is equal to d, the real parts of the imaginary number are the same. Only way you can get that, okay? If a is equal to c and b is equal to d, okay? So if this was 2 plus 7i, and this was 4 halves plus 21 thirds I, those are the same because 2 is equal to 4 halves and 3 is equal to 21 thirds. 7 is equal to 21 thirds. That was it. Okay. They have to be equal. Now, we're just not going to do anything unless you want to see something done. Let's look at other operations. Well, let's look at the operations with complex numbers. What are our 4 basic operations? Adding, subtracting, multiplying. Don't do those 3 first, and then we'll come back and do the division. So to add or subtract 2 complex numbers, you add or subtract the real parts and the imaginary parts separately. Basically, it's a lot like binomials. In fact, you're going to see this over and over and over again. It's a lot like a binomial, okay? You add like terms, okay? Subtract like terms. So think of these as terms. They sort of look like terms. They're separated by plus or minus signs. So for 2 complex numbers, a plus bi and c plus di, written in standard form, the sum and the difference are defined this way. The sum of those 2 is a plus c is the real part, and b plus d times I, that's the imaginary part. The difference would be a minus c for the real part and b minus d times I for the imaginary part. Just like you would expect. Think of them as like terms. Real part, imaginary part. Add, subtract, whatever it takes. And again, your rules for signed numbers work, so use them, okay? Because all you're adding or subtracting are the real parts anyway, okay? The I is just that extension of it. It's like the variable. You add the coefficients and throw the variable along with it. So if it's not a variable, it's a real unit, square root of -1. So there is an additive identity in the complex number system, and that's 0, same as in the real number system. Okay, what that means, if you add 0 to any complex number, c plus di or a plus bi, whatever, add 0 to it, you still get the same number, additive identity. Furthermore, there's an additive inverse of the complex number a plus bi, and that would be, any guesses? Negative a minus bi, because when you add that to it, add this one to this one, you get negative a plus a is 0, plus b minus b is 0i, and sure enough, you get the number 0. So that's the additive inverse. Just like you would expect it to be, I hope. Okay? Now, we're not going to do these necessarily, but I want you to see if you can do that quickly. 4 plus 7i plus 1 minus 6i. 5 plus I. Very good. Everybody say, well, they're taking lots of steps to get there, okay? They wrote it without the parentheses, and they basically combine like terms. They even call it that, grouping like terms, the real parts together and the imaginary parts together. Whoops! See the typo? Yeah, they shouldn't have that I there. If it's in parentheses, they shouldn't have that. Plus 7 minus 6, I. That I shouldn't be there. I don't have to group them. So, error. I'm sure they got it right in the book. It's the guy here, and that's 5 plus I, just like you did. Okay? How about this one? Can you do that one quickly? 4, because your imaginary parts add to 0. So guess what? You can add to complex numbers and get a real number, which is also a complex number, but you can get a real number out of it. Okay? The way they call it, you can add two imaginary numbers and come out with a real. Just like you can add Justin to the class. Okay. Has anyone else come in since the call roll? Okay. And here's how they do it. They do the real parts, the imaginary parts. This time they didn't group the I in there, so that gives you 4 plus 0i, which is simply 4. Very good. Here's another one. Whoa, bunches of them here. What can you do with that? Say again? With one little change. Negative high I. Because you notice with your real parts, you have a minus 2, which is plus 2, minus 2, that adds a 0. 3i minus 3i, that adds a 0. All you got left is a minus 5i. Well, they're going to take a bit more time to do it, but they first write them all down, then they group them, and then they add those, and you get minus 5i. So you can add 2 or more complex numbers together and come up with a pure imaginary number. Okay? That's what they call that. Don't sweat this too much. It's all doable. How about that one? What would that be? Real part. Say that again. Okay. Okay, the real part is 0. Excel. Yeah, all that, and we get nothing from it, right? Okay. You write them all down. That's how they do it. Frankly, I do it a lot shorter than that. Add the real parts. 3 plus 4 minus 7. And then add the imaginary parts. 2i minus I minus I. Okay? And sure enough, that gives you 0. Okay. All that for nothing. Okay. Now, many of the properties of real numbers are valid for complex numbers as well. For instance, addition is commutative in both addition and multiplication. I think we've just seen how it would be work in addition. We haven't done multiplication yet, but it still works. Associative properties of addition and multiplication is real numbers, also in complex numbers. Distributive property of multiplication over addition works in real numbers. It works in complex numbers as well. Okay? Now, Now we get to multiplying. Okay? Now, I want you to remind me how you multiply, say, 56 times 32. Give me a blow by blow. How do you multiply those? Okay? Get a pen out. Again, I'm probably spending too much time with this, but just in case you ever run into it, which you probably will. What if you're multiplying 56 times 32? I just made up those two numbers. How do you do that? Oh, okay. You do it a digit at a time, don't you? You multiply this times that. That gives you 12. Carry a 1. 10, 11. 18. You're all used to calculators, aren't you? Okay. Carry a 1 again. 16. And then you add those that correspond to the same values. This is a 1 value. That's just 2. These are your 10s. That would give you 9. Your hundreds would give you 7. And your thousands would give you 1. Yeah, that's what you do. You multiply each one by the other, digit at a time. Okay? That's what we do when we're multiplying binomials. Of course, what do we used to call it binomials? FOIL. First, outer, inner, last. Yeah, okay? Made you happy, okay? And basically that's what you're doing here, only they're showing it as a distributive property. Distribute A times the C plus DI. That would be your first, and that would be your outer. And then the B times the C plus DI, BI times that, and that would be the inner, then times the inner, and then times the last. And that's exactly what you're doing here. I just set it up differently. What do you get here? A times C is AC. A times DI is ADI. But multiply the real parts together, just have the I on the outside. And over here you have B times C times I. But here you have B times D times I, which is I squared. All right? Okay, this is real. That's real. That's real, but with imaginary parts on that. But what is I squared? -1. These were imaginaries. This is real. Real times imaginary, real times imaginary. So these are imaginary. But this goes out real times real. And that becomes real. So then you bring this over here, AC minus BD for the real part, and then add these, AD plus BC times I, that's your imaginary part. So that's how you do your multiplication of complex numbers. You FOIL them, just like we did before, but every time real times real will be real, and imaginary times imaginary will also turn out being real, but it will be the opposite sign, the negative of B times D. Then the other parts, the middle parts, the innards and the outers, just like we did. So rather than trying to memorize multiplication, simply remember how you use the distributive property. Even easier, FOIL it! It's always binomials. Real plus imaginary, real plus imaginary. It's always going to be 2 terms by 2 terms. So FOIL it. Makes it much easier. Okay? Now they're going to do a couple here. I think you can do that one in your head. What would that be? -8. Got it. Okay? They are going to distribute and do all this stuff, but they get -8 plus 12i. Okay? How about this one? Okay, that's a little more involved. How would you start? 2 times 4 is 8. Now, because I cheat, you know, let's jump to the imaginaries. Let's go straight to the last. First and then last. What's last? Well, the last. Yeah, those two. Plus 3. So 8 plus 3 is 11. Now do your innards and outers. Plus 2i. So what did we wind up with before? 11 was it? Yeah. 11 plus 2i. Okay. Take your time and do it, but that's what you're doing. So you see, you FOIL it. If you FOIL it, you get this exactly. First, outer, inner, last. Okay, that's you don't have to do that. Just FOIL it, and you get that. Okay? And then you notice that last term is -3 times -1, so that's plus 3. Combine that with the 8, that's 11. And combine the 6i and the minus 4i, and that's 2i. 11 plus 2i. So it's really just as easy as multiplying two binomials. Just remember, I squared is what? -1. Okay, so whatever that last product is, of the last, change the sign, you got it. Okay. See if we can do it that way here. First term? 9. Let's do the last next. What do you get? Do the last. Second? -4i squared, which is plus 4. So 9 plus 4 is 13. Now let's do the innards and the outers. 0, because this is minus 6i plus 6i. That adds a 0. So guess what? You get multiply two complex numbers together with imaginary parts, and you wind up with a real number, 13. Now, was there anything special about these two numbers? Okay. Okay. You're right. Okay. If these were regular binomials, that would produce the difference of two perfect squares. What it produces now is the sum of two perfect squares, because this I squared is -1. Okay? So, yeah, you're sort of right on the money there. But notice you multiply two complex numbers together, get a real number, strictly a real number. But these have a special name. Have y'all run into it before? Same number here, opposite numbers there. A conjugate. This is called the complex conjugate. Back when you did radicals, if you had square root of 3 plus the square root of 2 times square root of 3 minus the square root of 2, you would have these two multiplied together. That would give you 3 minus 2, which you'd lose your square roots. Guess what? Multiply complex conjugate together, you lose the i's. Okay? So, yeah, it's a pretty, and when you multiply two real numbers together, you have a difference of two perfect squares, which is a nice thing to have anyway. So, always multiplying these conjugates by each other, that's going to get you from a complex number to a real number. Now, where might you think we would really love for that to happen? If you remember back when we were doing conjugates with radicals in them, what do we never want to do? You can add radicals, you can subtract radicals, you can multiply radicals, just like we've done these. You don't want a radical in the denominator. So how do you get it out of the denominator? Multiply by its conjugate, and you lose the radical. Guess what we're going to do next? Divide complex numbers multiplied by the conjugate in the denominator, and you make it a real number. That's exactly how we do. Oh, here's one more before we go any further. What would that be? Well, let's write it down. 3 plus 2i squared. That's 3 plus 2i. That's 3 plus 2i. What does that give you? Okay. 9 minus 4 is 5, and then plus 12i. You got it. Perfect. Okay? Now, again, you're not responsible for this. Don't sweat it if you're not as fast with it. But, yeah, that's exactly what you get. Notice that squaring a complex number doesn't lose its complexity. It stays a complex number. It's just a different complex number. Boy, they take a lot of steps to do it. But they finally get there, 5 plus 12i. So squaring a complex number will not lose the imaginary part, okay? But multiplying a complex number by its conjugate, you will lose the imaginary part, okay? So that's where we're going to talk about complex conjugates. That previous example 2C that we did, these are called complex conjugates. If you had an a plus bi and you want to multiply its conjugate, keep the a, change the sign of the bi, okay? If you started with a minus bi, what is this complex conjugate? A plus bi, okay? Keep the first, change the sign of the second, okay? And what happens every time when you do this, and this time we're doing it not with numbers, but with letters that represent numbers. You're fulling a squared, outer minus abi, inner plus abi. There goes your i's, except for the last, and the last is minus b squared times I squared. But guess what? I squared is negative 1, so that makes it a squared plus b squared. Okay? Now, do you remember back when we were factoring and you could factor the difference of two perfect squares because those were the product of the conjugates? Now we can factor the sum of two perfect squares by their complex conjugates. Square root of this plus bi plus the square root of that I, square root of these minus the square root of that I. So now we can factor sum of two perfect squares where we didn't used to be able to. Oh, what a joy. You've been wanting that, haven't you? Yes, okay. Now, to write a quotient, a plus bi and c plus di in standard form, where c and d are both not 0. We can't ever divide by 0, not even in complex numbers. Multiply the numerator and the denominator by the complex conjugate of the denominator alone. Don't worry about the numerator. It takes care of itself. But multiply that denominator by its conjugate. But if you do that, you must also multiply the numerator by that same conjugate. Not its conjugate, but the denominator's conjugate. Why? What's this? C minus d1, di over c minus di? 1. And when can you multiply by 1? Anytime you want to. It doesn't change the value. All right, it messes up the numerator a little bit, okay? Still a complex number. AC plus BD, remember, because the I squared is minus 1, so that becomes that, and then you get minus ADI plus BCI, so BCI minus ADI, BCI. So it's still just a complex number. Maybe a little more complicated coefficients, you might say, but the denominator always becomes c squared plus d squared. Because multiplying complex conjugate, you lose the imaginary part, and the second part here changes. So now, guess what? This is real, that's real. So this is that, that's the real number. This is real, that's real, this is that's the real number. Fractional number, but okay. And that's times I. So you now have it in standard form. Whoa, they didn't show that, did they? They should have, but they didn't. They'll show it here, and again, we're not going to do it in gory detail. But what's the first thing you do? Of what conjugate? Of the denominator, which is 4 plus 2i. So multiply both the denominator by that and the numerator by that. Okay? Numerator is a little messy. That's 8 minus 6, right? Taking the I squared, 8 minus 6 is 2. And then the imaginary parts would be 4i plus 12i, so that's 14i. So 2 plus 14i. Okay? The denominator, though, is 16 plus 4, 20. So that would be, what was that numerator again? 2 over 20, which is 1 over 10, plus, I believe this was 14i over 20, which is 7 over 10. 7i over 10 or something like that, okay? Let's see how they do it. They carry it out long ways. That becomes that. Wow. Okay. Taking their time doing it, which is fine. Take your time in doing it. So 2 over 20 plus 16 over 20i. And that 2 over 20 is 1/10. 16 over 20, I said 14 over 20. 16 over 20 is 4/5 I. There is your standard form. Guess what? These don't have to be whole numbers. They don't have to be integers. They can be fractions, decimals, rational, irrational, anything you want them to be, just any real numbers. 1/10 plus 4/5 I, that's your standard form. Okay. 12 plus 4 is 16. How did I miss that? Okay. Complex solutions of quadratic equations. Okay. We've only dealt with the imaginary unit, I is equal to square root of -1. What do you do if you have square root of -3? That would be the square root of -1 times 3, right? So that would be I times root 3. Now this book likes to write it in standard form, put the square root of 3, then the I. I don't like to do that. Does anyone have a guess of why I don't like to do that? Yeah, if you're a little sloppy with your line here, you can't tell whether the I is inside the radical or not. So I like to put the I on the outside in front so it's patently obvious that's where it belongs. Sure, it's not quite in standard form, but at least you remove the ambiguity. So I would write this as I root 3. I know it's not standard form, but it helps me avoid making errors. And I always like to do that. Okay. So avoid making errors, not making errors. Okay. Principal square root of a negative number where a is a positive real number. The principal square root of negative a is defined as square root of a I times root a. I just cannot make myself write it that way, because it's okay in typed print because it's fairly easy to see. But boy, if you got that line going out there and it goes a little too far, you're not real sure whether the I is under there or not. So they're going to solve this. How would you solve that if you had to? Well, let's see if we can factor. Would that be factorable? Oh, excuse me. Let's say only possible factorization for 3x squared. 3x times x, right? Then we look where? Sign of the last term. Plus, that means these two signs have to be the same. They don't have to be positive. They have to be the same. Look at the sign of the middle term. Minus. So that means both of those have to be minuses. Now, what's the only possible factorization for 5? There's actually 2. 5 times 1 and 1 times 5. Okay? If you put the 5 here and the 1 there, then when you FOIL it, you get 3x squared, that's no sweat. You get the plus 5, that's no sweat. But you get minus 3x minus 5x is minus 8x, not minus 2x. If you put the 5 over here and the 1 there, it's even worse. Minus 15x plus, minus 1x minus 16x. No way that's going to factor. So if it's not factorable, what do we use? Quadratic formula. What does that give us? X is equal to what? Quote it for me in letter form. Minus b plus or minus the square root of b squared minus 4ac all divided by 2a. Okay, what in the world are A, B, and C? Help me. A is your 3. B is -2. C is 5. So let's plug them in. Minus a -2 is 2, plus or minus the square root of, and what's b squared is +4. Now, what I do next, I usually write them out. I'm going to do it as fast as I can now. You got one minus sign there, right? Then you look at your AC, plus and plus. So this is just going to be a minus. I always count my minus signs. If you get an odd number, it's going to be minus. Get an even number, it's going to be plus. And then multiply 4 times A times C. Ew, what do you get? 60. Okay, over 2 times 3 is 6. What about that 4 minus 60? -56. Okay, 2 plus or minus the square root of -56 over 6. Okay, guess what? Not a real number. Okay, and before that's how we would end it. No real solution. Okay, now we can actually do that. And I'm not going to go any further. Well, I probably will. Factor out the -1. That is the square root of -1. I. And then you have the square root of 56. You can factor out a 4 out of that, can't you? 4 times what? 4 times 14, is that what you said? Yeah, that's right. And square root of 4 is 2, so it'd be 2 plus, okay. I said I wasn't, but I'm going to. 2 plus or minus, and you factored out a 2i times the square root of 14. Okay, over 6. Guess what? Have factors of 2 here, so they go out, and that leaves you a 3 here. So this would be 1/3 plus or minus, and again, I like to do the I in front, the square root of 14 thirds. Okay. Now, maybe that one, you'd be safe to put the I on the outside of that, possibly, but still with radicals, I like to put it on the inside. That is your answer. In fact, those are your 2 answers. Okay? And the first one is 1/3 plus I times root 14 over 3. The other is 1/3 minus I times root 14 over 3. Or root 14 over 3I. Okay. I wasn't going to do that, but I did it. Sorry. Okay. Let's see how they do it. Yeah, they go straight to the quadratic formula. They knew. And that's exactly what we got. And that's exactly what we got, except I like to put the I before the radical, not after it. But that's perfectly fine. And so that's 1/3 plus or minus root 14 over 3i. There it's a little easier to see the I is under the radical. But you have to be careful how you write it. And that's it for this section. Again, you're not responsible for this on the test. However, we will be doing something in this next section and stuff that refer to complex numbers, but I'm going to try to avoid giving you too much that actually require them. Okay? I hit the wrong key. Okay, that's the right key. All right, we're through with 2.4. That was sort of, well, I thought I was rid of that. Okay. Yeah. It went back to 2.4. This thing is so. Here we go through this again. All right. So this is our chapter. And, whoops. 2 I was already in my trig class. Okay, 2.5. This is really what we need. This is the heavy-duty stuff. No, it's not that heavy-duty, but anyway. And it's sort of why we needed that 2.4 in there. We're still doing polynomial and rational functions. In fact, this is the last section on polynomial functions. The next section will be rational functions. So here we got zeros of polynomial functions. Now, this fundamental theorem of algebra references complex numbers, and that's why you needed it first. So we'll use the fundamental theorem of algebra to determine the number of zeros of a polynomial function. Then we'll find the rational zeros of polynomials. Rational, remember, ratio of two integers. We'll find the technique for doing that. We will, and we won't focus on this, but you will see that complex zeros of certain polynomials always show up in conjugate pairs. That's why I wanted to at least familiarize you with that nomenclature. Then we'll find the zeros of polynomials by factoring. We'll use the Descartes rule of signs, the upper and lower bounds rules to find zeros of polynomials. All these are tools to put in our tool belt so we can solve quadratic equations, okay, and polynomial equations. And then we'll find zeros of polynomials in some real life applications, okay? So let's start with the fundamental theorem of algebra. Here you've been in algebra how many years, and you probably have never run into the fundamental theorem of algebra. Why? Because it deals with the complex number system, okay? In the complex number system, every nth degree polynomial function has precisely n zeros. Was that true in the real number system? Every nth degree polynomial has at most n zeros, but it may have fewer than that, okay? Now we know that every nth degree polynomial function has precisely n zeros, but any of the real zeros are going to be complex. In other words, have real imaginary parts to it. So that's why we weren't able to say. But and we'll notice this later. Remember, if you think about it before, they were always off by 2, or so multiple of 2. And that's because the complex parts were conjugate pairs. But we'll get there. This is a Pointer result is derived from the fundamental theorem of algebra, first proved by the German mathematician, one of the incredible minds in mathematics, Carl Friedrich Gauss. So if someone hasn't chosen a paper topic yet, he's incredible, okay? There are many others that are too. Many people rate him up with probably Archimedes and Newton as being the top 3 mathematicians of all time. Incredible mind, okay? And here's the fundamental theorem of algebra. Really is not that impressive, except to be incredibly difficult to prove. He first proved it. So the fundamental theorem of algebra, if f of x is a polynomial of degree n, just like we started there, as long as n is greater than 0, so we're not dealing with f of x equals 3, not that, okay? Then f has at least 1 0 in the complex numbers. We just said up here it has precisely n. Well, you got to start with 1. So that's the fundamental theorem of algebra. Okay? That sounds awfully innocuous, doesn't it? Well, so what? But that's where it all begins. Okay? It may not even be a real 0. It may be an imaginary 0, but it always has at least 1. And then from there, you can show that it has precisely n zeros. Okay? So, using the fundamental theorem of algebra, we're not, but they do, Gauss did, and the equivalence of zeros and factors, we can obtain a linear factorization theorem. Okay, now this is doing things backwards from how we usually do. Remember, we tried to do that last quadratic we had. We tried to factor first. If we could have factored and had that these two times this times that equals 0, then what would be our next step? If we had x plus 3 is times x minus 5 is equal to 0, what's our next step? Yeah, set each of them equal to 0, x plus 3 equals 0, so x equals minus 3, and x plus 5 is equal to 0, whatever I said, x equal to minus 5, whatever the thing is. That's exactly what we would do. 0, that means x equal 3 is a 0. This is the factor, that's the 0. You change the sign because you move it to the other side of the equal sign, right? Well, that's what we're doing here, but in reverse. So if we know that we have n zeros, then we have n factors, because every 0 can be set aside as a factor. Just move it back, change its sign, and make it a factor. So if f of x is a polynomial of degree n, where n is greater than 0, then f of x has precisely n linear factors, because it had precisely n zeros, it now has precisely n linear factors. And the f of x may have some coefficient in front, a sub n. That sort of may be particular to that one. But then you have x minus c1 times x minus c2 times x minus c3, all the way up to x minus c sub n. Okay? You have n of these factors. Now, why do they call them c's? They're complex numbers. Okay, yeah, they're constants, you're right, but not just any old constants. They are complex constants. Of course, what is included in a complex number? Any number. Real numbers are all complex numbers. So these could be real, or they could have imaginary parts. But you have precisely this number of factors, because in every one of them, if you set that equals 0, then x is equal to c1, x equals c2, up to x equals cn. You have that many zeros. Okay? So the earlier thing we said it has precisely n zeros. This says we have precisely n factors. You could have a constant out in front too. It's not really a factor because that's not a solution, in any way. Note that the fundamental theorem of algebra and the linear factorization test tell you that the zeros or factors of the polynomials exist. They don't tell you how to find them. Okay, that's up to you. Okay, so these are called existence theorems, and those are usually pretty hard to prove. Okay. Finding them, though, sometimes that can be a little difficult as well. But that's what we're going to do, basically, the rest of this section. Okay? All right. So here's the first degree polynomial. What does that tell us? First degree, it has exactly 1 0. How do we find that 0? Set it equal to 0, and then you solve it, and what do you find? X equal 2. There it is. We've already been doing that all along. Tells us we have exactly 1. That could have been complex, but it wasn't. It was real. Okay? Well, reals are complex too. Okay. How about this one? Here's the second degree. How many complex zeros could you have? Or zeros could you have? You're going to have exactly 2. What are they? How would you do that? Okay. My hearing's so bad I can hear. Ooh, wait. Let me get my color back. Okay. We set it equal to 0 to find the zeros of the polynomial function. Set it equal to 0. Then we try to factor, setting that equal to 0. What did you say we'd factor as? X minus 3 times x minus 3. So what are your zeros? X equal 3 and x equal 3. Counting multiplicity. We have 2, they just happen to be the same ones. We didn't talk about that before, but that's legal, okay? You can recommend that many factors, 2 factors. Each one of those has a solution of x equal 3. Same number, but that counts because of multiplicity. You can count that twice. Okay? That's how we did it. I think they do it pretty much the same way. Let's see. X times 3, x minus 3 times x minus 3 has exactly 2 zeros. One's x minus 3, x equal 3, the other's x equal 3. So like my brother Daryl, my older brother Daryl. Okay? Same type thing. Repeated 0. Okay? How about this one? How many zeros you think we're going to have? 3, exactly 3. Complex zeros. They could all be real or not. What would you do first?
Second? Factor out an x, and that leaves you x squared plus 4. Any bells, whistles going off? Red flags flying? Those two are going to be complex. You set it equal to 0. This is going to be x equals 0, and this is going to be x squared plus 4 is equal to 0. Now we know what to do now that we had the previous section. I'm not going to require you to do this anymore. I'll try not. But if you ever have to, you could then say x squared is equal to, subtract 4 from both sides, a negative 4, and then what would you do? Yes, x equal plus or minus 2i. Okay? Because the square root of negative 4, take the square root of both sides, square root of x squared is x, square root of negative 4 will be square root of negative 1 times 4, square root of negative 1 is I, square root of 4 is 2. Okay? But plus or minus, there's your 2. Plus 1, there's your 3. Only have one real, but you have two complex. Well, imaginaries. Okay. So let's clear that out of the way. Again, I'm going to try not to ask you any that require you to do that, but they went through the same steps we did. Now, they factored it. Frankly, I see it better doing the way I did, but certainly that's a possibility as well. It's a complex conjugate because this didn't have any i's in it, so it has the factor of the conjugate, x plus 2i times x minus 2i. You're not used to doing those, but there's your exactly 3 zeros, x equals 0, x equals 2i, and x equals minus 2i.
With that x squared plus 4, you couldn't just do x plus 2x minus 2 that way?
Okay, you said you thought this might factor as x plus 2 times x minus 2. Try it. X times x, sure enough, gives you x squared. X times minus 2 is 2x plus 2x, 0x. That's certainly right. But then you get a minus 4, not a plus 4. Yep. Put the i's in there, you got it knocked. Yep. Exactly that. Okay. So this one won't work, but it's worth a try. Okay. All right. This is what we're a little more interested in, and this is the rational zero test. Okay? Let's at least introduce it here. Okay? The rational zeros test relates the possible rational zeros. Now, these are rational, not just real zeros, not even real, only the rational zeros of a polynomial, as long as this polynomial has integral coefficients. Now, so far, that's all we've been dealing with. But if you have fractional coefficients, you can't use this test. If you have irrational coefficients, you can't use this test. It has to be integral coefficients. And so far, all the polynomials we've dealt with have been that way, but in real life, they're not. Okay? You can have all sorts of decimal coefficients and stuff, but right now we're just dealing with integral coefficients. So it's sort of a limited test, but it's one we use a lot. And what it does, it relates the possible rational zeros to only 2 terms. This could be a 16-term polynomial, but you only look at the leading coefficient, that a sub n, and the constant term at the end, your a sub 0. And those two themselves will, yes, ma'am. Okay, we are almost through. We got 1 minute. Okay, you can have a seat if you like. Okay, so those, we're going to determine at least the possible rational zeros just from leading coefficient and constant term. So here's what the rational zeros test says. This polynomial, f of x, a sub n, remember that's just a coefficient. The n just tells you if the coefficient goes with the nth power of x. A sub n, x to the n, a sub n minus 1, times x to the n minus 1. So it's just identifying, I go with that one, okay? That's what the subscripts mean. Count on down till you get a2 times x squared, plus a1 times x to the first, plus a0 times x to 0, which of course is 1, so it's just a0. It has, as long as all these a's are integers, positive, negative, no fractions, no decimals, but it could be zeros too. Some of those could be zeros. Not the first one, but the others could be. Then, every rational zero of F. If there are any rational zeros, they're going to be of the form P over Q. Where is P or Q coming from? Well, P and Q have no common factors other than 1, and P is a factor of the constant term, and Q is a factor of that leading coefficient. So what you do is write the constant. What I do is write the constant term of the leading coefficient, and then factor each of them as much as possible. If there are any common factors, eliminate those. But those factors that are left. And I'm afraid we're out of time, so we'll leave it at that, and we'll pick up next time with the next slide, which is this one. Okay. We'll pick up that. Okay, you mean right now?
Yes, sir.
Oh, yeah.
Right now.
You got 15 minutes between classes if you got another class.
It's for you.
The cafeteria, you
Yes,
said?
sir.
Okay. Not the faculty dining room, but the cafeteria itself.
The faculty dining room.
Faculty dining room right next to the cafeteria.
Yes, sir.
Okay. So if you got a chance, go down there. Sorry, I would have given you the last 2 minutes. I thought you came to see me. Okay. Yeah.
And they're on good time. I'll come with me for a few minutes.
Okay. All but can.
Time.
Yeah.
A few minutes.
Okay. Good deal. I didn't give you your homework assignment. I'll put them on Screencast-O-Matic though. You won't have many out of this. Try to do any of the odds 9 through 13. That's all. 9 through 13. Any of those odds. Okay. Good deal. Boy, y'all got off easy today, didn't you? Okay, fantastic. Okay. All right, first second quiz in. Okay, good deal. Okay. When is the next test? When we finish 2.6. So we just got started in 2.5. We'll finish 2.5 and then do 2.6. I'm guessing so. We're not going, yeah, definitely, yeah. Because Thursday we're going to continue in this. Okay. Wish we could go longer, but they're making us take a spring break. Boo hiss. Right. I was expecting the Tyler to really chime in with that and say, yeah, what a ripoff.